Nicolas Randazzo, welcome to the podcast.
Glad to be here. Looking forward to it.
It's funny because during our email exchanges, you told me to just call you Nick. And it's
Yes.
funny because when I see your last name, I want to call you Randazzo just because it's cool.
You know what? I'm fine with it. I have been called Rendazzle before. I've been called Randall before, so
That's
whatever
hilarious.
you want to call me, it's fine.
I'm just being playful.
Yeah.
So you are a PhD candidate at Master University in Hamilton, Ontario, Canada.
Okay.
You're actually a colleague of one of my former guests, Ben Pierce,
Yeah.
who's just awesome. And your specialty, however, is paleoclimate.
One of my multiple specialties. Yes.
Okay,
Yes.
right.
Yeah.
So what are your other specialties?
Um, well, I'm first and foremost a stable isotope geochemist, but I apply this to sedimentology, just regular plain geology, but then also I have a lot of applications with the paleoclimatology and astrobiology as well. That's how I know Ben.
Wow, so that's a lot for a PhD candidate. What is
Yeah.
your actual like PhD focus on?
So I have three PhD projects that I'm working on and three that are side projects. Yeah,
Are
I
you like
know.
superhuman or something?
Um, I think I'm more just insane. I think that's
Oh,
probably
okay,
more
okay,
correct. Yeah.
fair.
Yeah.
Go on, sorry. So what
Yeah.
are the 3 projects?
So my one project is actually trying to reconstruct the global sea level during the Turonian. The Turonian is just it's a really hot period of the Cretaceous. So like in my field, say we go and we find dinosaur bones and dinosaur footprints and things like that. But basically, we're trying to see if back then, like the average surface temperature, sea surface temperature was like 35 degrees, was significantly hotter than it is today. There were crocodiles and flowers up in the Arctic, but one of the questions is, could ice still have been present in Antarctica at this point in time? And some of the research says the coast waters around the continent of Antarctica were probably too warm, but we think there could be evidence of ice within the continent. And the only real way we can do this is try to find evidence of freeze thaw cycles. So, because these ice sheets in Antarctica, they're so big, when they melt, they add a significant amount of water to the global ocean. So, sea levels actually rise a significant amount. And if we try to pair that with Milankovitch cyclicity, we can try to see if there's some sort of periodicity. So, like, are we having sea level changes that are on the order of, let's say, 100,000 or 400,000 years, which is in sync with Earth's eccentricity? Or if there's like an obliquity, the Earth's like the angle in which the Earth tilts. Like right now, it's at 23.5, but that changes every 41,000 years. So just trying to find with using age dates and things like that, if we can pair that with sea level to find evidence that there was actually ice, and then this has implications towards like global warming. Like this place was significantly warmer than it is now, but there was still ice. And then my other projects are either using geochemical proxies, which I'll talk about later, to help reconstruct the environment. So, like, what was the atmospheric CO2 pressure like at the time, or what was the temperature that things were deposited at, or what were the oxygen levels in the water column that my sediment core that I'm taking all my samples from was like. Was it anoxic, in which case we're getting a lot of organic carbon preservation, or was it oxic, in which case all those little plankton and things that die when they fall to the bottom, are they just decomposing and then that's it, and it's perfectly fine. So, and then that also has implications towards biosignatures and petroleum exploration. And yeah, it's mainly just a paleoclimate. Uh,
Yeah, so I mean, I had like maybe 10 questions in your first 5 sentences. So, for me, what's most interesting here is that the Earth, regardless of man-made activity, let's say, the Earth
mhm.
has because it has evolved, obviously, right? I
Yep.
mean, like you said, every 40,000 years, there's a massive shift.
Well, yeah, there's multiple things that affect multiple things affect climate in general, but in terms of like Milankovitch cycles, there's basically like the Earth's wobble changes. So there's a 23,000 year cycle for that, and then the tilt is 41,000 years, and then the eccentricity has its own like 100,000 as an example, 100,000 year
Do
cycles
we
as well.
know? what causes this stuff? Like, why does the Earth wobble all of a sudden?
Yeah, it's basically just interactions with other planetary bodies. So, like, the Earth's eccentricity around the sun is affected by, because it's not just Earth that's revolving around the sun. Like, there's Jupiter and there's Saturn. So, like, Jupiter and Saturn's pull on the Earth over time can add up and change things, or like the gravitational pull, like of the Moon, or just like Mars and Venus, which are also close, or the Sun itself, which also kind of wobbles.
So
Yeah.
is this like a butterfly effect, as in if somebody were to, I mean, an alien life form were to blow up Jupiter, would that
Oh,
obviously impact us?
yeah, we'll probably, like, die. Jupiter catches so many asteroids for us that, if Big Brother's not there to get rid of those asteroid bullies, yeah, we probably won't last too long.
Okay, so that's interesting. I didn't actually know that we were so dependent on other planets, like
Mhm.
if Saturn's axis or rotation were to stall or something, or even if I would imagine even if the rings of Saturn were to be affected, that could impact Saturn itself, and which would then butterfly affect us, right?
Potentially, yeah. Like, there really is a lot of, like, I guess, a synergy between all the planets, and that actually allows life to exist, right? And these are some of the questions that we have when looking for evidence of life on other planets, right? It's not just like, okay, how close is it to their star? Is it close enough for liquid water? Therefore, it must have planets. Like, well, no, no, no. Does it have, like, tectonics? Is that something that we may or may not need? Which we thought the answer was yes, because volcanism introduces, like, CO2 into the atmosphere, creates, or like into the air of the planet, creates an atmosphere, and then you allow greenhouse, like, warming to happen, basically. But there's also a thing called a stagnant lid planet, in which case it doesn't actually have active plate tectonics, so that may not necessarily be a requirement. But there are things like, do we have a planet that can help catch asteroids so nothing hits it? What's its atmosphere like? What's the size of the planet, right? Like, Mars is really small and ended up, actually, it's geologically dead now. Well, we think, for the most part, and it doesn't have a magnetosphere now as a result of that. And now its atmosphere was stripped away by solar winds. So now, the atmosphere, Mars is like 6 millibars, where before you could have been like 500 millibars, or could have been like into the bars, could have been much higher. But yeah, like, there's all these different factors that we need to consider, that a lot of times we might not really think about it, but there really is like a little butterfly effect, that if you change one thing, it might make the difference between a planet being habitable to going to not so habitable.
Are you able to tell by looking in the past where we're at now? Like, where are we in terms of like when the Earth might rotate, like do this axis rotation stuff? Like, are you able to know, like, okay, this is actually we're in for another ice age, for example?
Yeah, actually, we have a really good understanding of, um, pretty much everything that affects Earth's climate, like, not just the orbital cycles itself, but also, like, solar cycles. Or we have a really good understanding of tectonics and the effects of volcanism. And one of the major things that my research looks at, like paleoclimatology, is looking at these things called climate archives, and how we can reconstruct the climate from millions to even billions of years ago and get an understanding of what Earth would have been like. And because we have this understanding of how climate has changed in the past, we can actually make inferences to the current climate change, right? So, like, for any listeners that aren't really certain, like, the global warming being caused right now is undoubtedly caused by humans, like us releasing those greenhouse gases. Like, I we have a model of how climate has changed, how temperature has changed, over the past few million years, and the current rise is quite significant. Like, it's unlike anything that we've seen, like, between the industrial age to now, like in 200 years. Like, temperature has increased significantly. The amount of CO2 in the atmosphere has increased significantly. So we actually have a much better understanding of the past than I think a lot of people think.
And that is actually one of the things I did write down, which is
Hmm.
because I don't like, pretty much shitting on people who don't believe in climate change or whatever, because I think there's a chance for us to explain certain things. And I think, the people that I am aware of that are climate change deniers, let's say,
Yeah.
are people who know. who believe climate change is real, but they don't yet believe that it's caused by man. They think,
Hmm.
oh, well, the Earth goes through these cycles every, X amount of thousands of years. I mean, this is just a natural occurrence and blah, blah, blah. And then NASA just recently announced that the moon is wobbling and that's going to cause rising sea levels. So it's the moon's
Yeah.
fault. It's not our fault. But what you're saying here is really interesting. You're saying, well, actually, yes, Earth does have a tendency to warm and change and
Yep.
cool and all these things, but the what's unprecedented is at the level it's at,
Correct.
right? Compared to the past, and you've been looking, like, how far back have you been looking?
So my research specifically only goes back 90 million years. It's
Only
only
90,000,000.
yeah,
Yeah.
but like we have like climate archives that can go back way further. So I've said the word climate archive. It's basically any sort of material that just by its nature is able to retain some sort of climatic evidence. And like these archives might be like ice cores or sediments or corals or tree rings or foraminifera. And basically, like in the case of ice cores, um, when they form, like we can look at the banding of the ice cores, which can tell us a little bit about like if it's summer, if it's winter. But then there's things like um, gas bubbles that get caught. So we can actually take measurements of the atmosphere because this gas bubble got caught in the ice, let's say 200,000 years ago, and it's been there this whole time. And now, like you and I go out to Antarctica and we drill a core and there's these ice bubbles, and we can actually sample the gas that was stuck in there. Or you can look at things like the pollen record. So, like oak, as an example, grows in very warm climates, but then there's like prairie grass, which grows in dry climates, and spruce that's a little bit more cooler. So if you start looking at the pollen record throughout, let's say you have lake sediment, or let's say you have an ice core or something like that. Let's say lake sediment will probably make more sense. But you can start looking and say, okay, well, we know we age dated it, so we know the approximate dates. And 10,000 years ago, there was a lot more oak pollen, implying that it was warm, but then all of a sudden the oak pollen starts to decline around, let's say 8,000 years ago, and prairie grass goes up. So now it was a drier climate. And then let's say 2,000 years ago, spruce was a lot higher. So now we went to cold. So we can actually start making these comparisons. And then my research primarily focuses on stable isotopes, but I also look at also use like energy dispersive X-ray fluorescence. So you can look at actual elements within a core itself, and then certain elements will be present under certain environments, just because they might form molecules that just tend to last at a certain time. So, like manganese, if I'm looking at a sediment core that was underwater, would be very prominent during oxygen-rich environments. But then I can start looking at things like um, let's say molybdenum and vanadium go up, and then that could appear in more anoxic or even oxinic. It's like sulfur rich. So it's not only there's not a lot of oxygen in there, but there's also a lot of like um, bacteria that like sulfur reduction is occurring as well. So like we can do that. And in terms of looking at stable isotopes, so stable isotopes are different from radioactive isotopes. So radioactive isotopes like uranium 238, they go under a radioactive decay. So they'll slowly like they'll decay into daughter products. So like uranium will become thorium, and then that will decay further. Whereas stable isotopes, they're exactly that. They're stable. So their concentration in the environment doesn't change. So like oxygen 18, if there's oxygen 18 in something, it will always be like that. The oxygen 18 isn't changing to anything.
Okay, I'm
So
gonna stop you right here
yeah,
because I'm a little lost now because you're
sure.
you're now talking about isotopes. Why are we talking about isotopes? What is it that you're looking at exactly?
Yeah. So okay, I'll rewind a little bit too. So isotopes, basically, for anybody who doesn't know, they're atoms that have the same number of protons, but there's the neutrons are different. So like the typical oxygen isotope has oxygen, it's oxygen 16. So there's 8 neutrons, 8 protons, making 16 if you add the 8 and 8. But then there's also oxygen 17 and oxygen 18. So let's say in the case of oxygen 18, there's 2 more neutrons in that. So that's a stable isotope of oxygen. And basically what happens is these things are the environment, and certain processes will actually cause a preference of one isotope over another. So these are called like these are kinetic fractionation. So like evaporation, when water evaporates, it will preferentially evaporate water molecules containing oxygen 16 rather than oxygen 18. Or precipitation will prefer oxygen 18 over oxygen 16.
Okay,
Photosynthesis, yeah.
so if you're measuring isotopes essentially it's telling you if water is going up, going down, evaporating, whatever. These are markers is what you're saying.
Yes, yeah.
Okay. Okay.
So these are basically proxies. So we can actually look at isotopes within, let's say, foraminifera, or within ice cores, or within sediments, or within corals, and they can start to tell us things about the environment. And with like oxygen isotopes looks at temperature. So using that, we can look at the oxygen isotopes and tell what the temperature would have been like, let's say, at the time a coral was forming. Or
Okay, so you're, like, digging a hole, like you said, like, you and I take off, we go to, Antarctica, we bring this, like, giant tool that can actually bore, like, a big ice sample. From there, you're telling me that you can actually look at a layer of ice and be like, "Oh, yeah, it was, 12 degrees, Celsius at this time of year in, whatever year BC," kinda thing. Is that what essentially you're getting at?
Yeah, basically, especially if you're looking at something with calcium carbonate, like you can definitely like a coral or a foraminifera, you can definitely tell the formation temperature. Ice, it's more like you can look at the air bubbles stuck within the ice core itself, or like things that are caught within the ice, like pollen or like dust and things like
Wow.
that. Yeah. Um,
Wow.
the thing with ice is like ice melts, right? So you can
Yeah.
only go so far. And then also after a certain point, the ice kind of gets deformed to the point where like it's probably not trustworthy. So like in Antarctica, you could get like an ice record that goes back like 800,000 years. In Greenland, it might be more like 400,000 years, but still, like, you can take, let's say, atmospheric samples from little gas bubbles in ice and know what the climate was like 400,000 years ago in the environment. Or if you look at things like corals, like you can see, like, okay, when this coral formed, this was what the temperature would have been like, and you can do that with any of the stable isotopes. Like they all have different, they're all proxies for different types of environmental parameters. Um, so like,
Wow, that is wild. Have you
yeah.
actually ever, like, been to Greenland or Antarctica? Like, have you actually held a really old sample of something that, like a coral or something or ice?
I've never been, unfortunately, to Greenland or Antarctica, but my field site is in like Utah, New Mexico area.
Okay.
So that's all like Cretaceous age dinosaur, time of the dinosaurs kind of stuff. But have I held stuff? Yeah, actually. Earlier today, we did a graduate student led field trip hike, just like looking at some of the geology of Hamilton, and a lot of these rocks are they're about 435 million years old, and you can like just walk along the Niagara Escarpment and you can start like picking out like crinoid fossils, and these are sea lilies that 435 years ago, when Hamilton was at like 20 degrees latitude and much warmer and much more tropical than it is today, you actually had like, and we were underwater at this point in time too. Like there's sea lilies, or you can have trilobites, which are like these little arthropod like creatures. They're one of the first creatures to actually develop eyes as we would recognize them. Yeah, so you have these little
I
fossils.
didn't know
So
that. I didn't
yeah.
know that about trilobites. It's interesting because I actually, I picked up a few I've been looking at rocks more and more. I'm kind of starting to nerd out on them now.
Oh
It's kind
yeah.
of like my new thing. And I picked up a rock full of just all these fossils, and like I think they're like the ones like crinoids and all that stuff. And
Hmm.
and I guess it makes sense because Ottawa was also, underwater
Yeah.
for millions of years or whatever. So you're gonna
Hmm.
get all these fossils. I guess it's really not that rare to hold something in your hand that's like millions of years old.
Yeah, it's really not. It's kind of unfortunate. We were underwater back then, but we weren't underwater when the dinosaurs were around. So any dinosaurs that were kind of walking around in Ottawa or in Hamilton, like they died on land and their bodies were all eroded away and they're basically gone. But then you go to like Alberta and there's these beautiful fossils that, yeah.
Yeah,
But
that's definitely one thing I wanna do is, look for, like, dinosaur stuff in Alberta one day, maybe go on,
yeah,
like, one of those tours or something, but
oh yeah, that'd be
yeah.
perfect.
Yeah, for sure.
Actually, yeah,
Okay, so you're studying all of these things about, the climate, so I'll go back to the question that I asked earlier, which is like, do we know where Earth is at right now? And what is the biggest thing that you would say from looking at the past to the threats for the future? What would be your concerns as a scientist? Obviously, man-made warming is
yeah,
a top priority, I think, on everybody's minds right now, or anybody who's a scientist at least, and hopefully more people
yeah.
out there in the world, politicians, etc. But outside of that, are there other things that are kind of like, oh, you're like, huh, this is interesting, this could be happening in the future based on what we know from the past?
Yeah, like there's always like concern, like asteroids hitting the Earth, or like um, coronal mass ejections from the sun being pointed at Earth and like wiping out our technology. Like there's always concerns like that. I'd probably say global warming is probably the biggest concern, that like earth scientists and environmental scientists are primarily focused at, and that's probably where the majority of our research into the past, its main application is to just basically try to understand the future, and just looking basically into the rock record, because that's the best record we have of what life was like back then at any time you're interested in, and actually studying what's the you know what happened back then and what are the implications. Another thing that's actually cool, just sorry to go back to isotopes again, are
Please.
the carbon isotopes. So carbon has a stable isotope that's carbon 12, and then there's that's like the regular version of carbon, we'll call it. And then the actual heavier version that we look at is carbon 13. There's carbon 14 too, but it's radiogenic. But we'll go back to that later. And carbon is basically photosynthesis preferentially takes in carbon 12, leaving carbon 13 into the atmosphere. But what's neat is when you start looking at things like go back to my research during the Cretaceous, plankton would take in carbon 12. They die. They fall down to the bottom of the ocean floor. And if they happen to be, let's say, buried, let's say there was a storm event or anything where they fell and sediment covered them up and there wasn't actually a chance for them to decompose, that carbon 12 that they took into their bodies gets actually locked away in the geological record. And then we can actually start to monitor things like we can create a stable isotope curve, and we can start seeing like, okay, when this isotope spikes here, that means one thing. When this isotope spikes in the opposite direction, it means something else. So we can actually look at these periods of anoxia, like low ox or no oxygen, versus oxia. But what's interesting too is those buried plankton are now our petroleum products. Like fossil fuels came from plankton. So when we burn those, we actually end up getting this very the way you measure isotopes is you put the heavier one on top, so carbon 13 relative to carbon 12. So we'll say carbon 13 depleted, because there's more carbon 12 compared to 13. So it's carbon 13 depleted fossil fuels or carbon being released into the atmosphere. And carbon 14, the radio isotope version of it too, is also useful just because carbon 12 decays after like 5,700 some odd years. So this carbon 12 from those organic matter that we've now releasing as fossil fuels is basically like carbon 12 or carbon 14 depleted, right there. That carbon 14 has now completely decayed. So we're actually releasing very carbon 13 depleted or also carbon 14 depleted carbon back into the atmosphere. And we know the volume of Earth's atmosphere and how much CO2 is in. So when you look at the isotopic composition of the atmosphere and you compare it to, let's say, carbon isotopes from, let's say, volcanism, which also releases a lot of CO2, but you can actually look at the isotopic signature of the atmosphere and you can start to compare. And this is one of the ways that we can confirm that, in fact, a lot of the carbon that's in the atmosphere causing global warming is, in fact, carbon that's released as fossil fuels. Like, it has an isotopic signature that matches like what we would expect from the burning of oil.
So that's the scientific explanation for when the news media says, "Oh, fossil fuels are to blame for climate change." That's the
Yeah.
scientific explanation, which is, well, it's because we're this molecule, I guess this carbon-13 is getting into
Mhm.
the is carbon-13 getting into the atmosphere, right? Or is it carbon-12 changing
It's
into 13?
well, it's carbon-13. We call it carbon-13 depleted, but it actually just means
Oh.
that it's rich in carbon-12 because it's depleted in 13, so it has more 12 therefore.
What does this actually do to the atmosphere? What this increase in this depleted carbon, what does it actually do?
So the carbon itself, like as a CO2 can as a molecule doesn't necessarily um, care if it's got carbon-12 or carbon-13 in terms of like global warming. Like, it's not necessarily like CO2 containing carbon-12 is more effective at trapping solar energy from the sun onto Earth's surface. Like, that's not necessarily the case. It's more about just it has a unique signature that we can now link to its source. And then people also do studies, like you can like move around, let's say compare Hamilton, Ottawa, Toronto. You can go to these different metropolitans, but then also go to these farming communities and you can look at the isotopic signature of the atmosphere and you can see like, okay, is there more of an influence from um, carbon-12, carbon-13? Like, is there more fossil fuels in the immediate atmosphere around there? Um, yeah. So sorry. Go ahead.
So, I guess the main question then is why does it matter if there's more fossil fuels? Like, what does it actually do to the atmosphere?
So the atmosphere, what it basically does is it traps heat. So Earth, um, there's long wave radiation that's coming from the Earth itself, but then there's the short wave radiation from the sun. So just like if you've ever been inside of an actual greenhouse,
Mhm.
like it's as soon as you walk in there, it's pretty hot and humid. And basically the reason is the sun from the the sunlight from the it goes through the glass and then actually gets trapped in there, so you can actually keep that heat. So that's essentially what's happening is there's these thick layers, there's this thick amount of gas that's now in the atmosphere. So CO2 is what we're talking about, but there's also like um, methane gas, which is actually like 25 to 30 times even more effective as a greenhouse gas um, than CO2 itself, and it traps heat, and then this heat has implications in terms of causing droughts, in terms of causing melting ice, which then could cause a positive feedback too, because ice is white and it will reflect sunlight, but as that melts and you start seeing, let's say, dirt or the ocean itself, which are darker colors, they'll tend to absorb even more solar energy. So it actually ends up further continuing this rate of melting. So that's called different changing in albedo. That also happens. So, and then you have the melting of ice, which is not only adding more water to Earth's oceans, causing sea level to rise, but then there's also something called thermal expansion. So actually, ocean water itself, just by being heated, will actually naturally expand just as the molecules go a little further apart from each other. So thermal expansion plus the melting of ice will now cause sea level to rise, which then not only causes problems for a lot of island nations, but it can also like, like New York City
I was just about
is
to
near
mention New
water.
York.
Yeah,
Yeah.
like if you start increasing sea level by, 6 meters, 10 meters, 20 meters, like all of a sudden places like New York gets submerged in water, or places in Florida. So like it's not necessarily just these island nations that which would be absolutely devastated if something like this happens, but it's also places that we're familiar with, that we have a lot of populations, like a lot of human population lives near the coastline or near rivers and things like that are going to cause that. Heating also, like I said, causes droughts, which can then lead to more forest fires. And we've seen fires in California and Australia, and even here in Ontario, we're getting fires. It's just there are so many different implications for life and not just human settlements, but then also like plants and
Animals.
animals. Yeah.
I interviewed David Johns, who's the head of the Continuous Plankton Recorder Survey out in
Oh.
England, and he was telling me about one case where they found a plankton no, a copepod, I think it was a
Oh,
copepod
okay.
that's, from the Pacific, and they found it on the Atlantic coast, and they discovered that they assume what happened is because of climate change, it actually went all the way above the Arctic and ended up on the east coast of Canada,
Wow.
somehow, which is obviously very interesting, and the data is very interesting. They have very, very old and very accurate data, over
Hmm.
there and just monitoring the plankton, right? Because that's another sign of things like global warming.
Oh,
What
yeah.
are the plankton doing? If they're moving around,
Hmm.
obviously, you wanna track and see that information. And then, all the things that you mentioned that global warming would cause. Compound that with, like, this recent news article about from NASA saying that the moon is wobbling and it's gonna cause
Yeah.
levels to rise in the 2030s, as though that doesn't compound the effect already, you
Well,
know?
absolutely, right? Like, yeah, the moon controls the tides. So if that's gonna now we're actually gonna have more tidal sea level, like tidal based sea level rise, compounded, like you said, with all this. Yeah, it's a mess, and I think a lot
It
of people don't
is.
know. Yeah, it's
Yeah,
yeah.
and that's one of the things I do like to bring up, science communication because when I first started this podcast and when I first started, A Tiny World, which I think you're
Oh, yeah,
familiar with, which is my microscopic project, I
yeah.
was really, gung ho about scientists doing SciComm. Now I'm having a little bit of a change of perspective, only because I've heard from scientists who feel like they're forced to do science communication, which I don't agree with. I
Mm,
think it should be a voluntary aspect to science, where a scientist who just wants to do research
yeah.
should be encouraged to just do his or her or their research
Hmm.
and just do their thing. Whereas scientists who are gung ho, like yourself, who are game to do SciComm, go for it. Great, awesome. That being said, I think there's a role for a middle person, for somebody who's a
Yeah.
communications expert to talk science. I want to know your perspective on this because I've had this conversation with a few scientists on this show, and I'd love to know, like, what are your thoughts on this new wave of science communication, and should it be a requirement?
I don't think it should be a requirement because I think one of the issues with science communication is science isn't always communicated very well. And I feel like if you're not passionate about it, like if you're being forced to do it, chances are you're probably not going to do that great of a job. Just because it's you're strictly doing it because you're forced to. So I think you need to be passionate about it because I think before anything else, people will sense your enthusiasm. And if you're really passionate about it, they might be more willing to listen to what you have to say, and they might be able to actually be able to maintain their focus. Because we've all had people talk to us that are monotone, and like you could be really interested in the topic, but if they're not enthusiastic, you can't help but start to maybe not listen as much as you would like to. So I think enthusiasm is important. The middle ground, I think, probably is a nice little sweet spot where it's yeah you kind of get the best of both worlds. I think I think we do need people that focus strictly on the research itself, but then there's also people that like doing strictly science communication is great for some people, but it is great to actually be like physically active in the field and not just say like, well, here's something that I've learned about and let's talk about it. This is actually something that I physically worked on myself, and it's really cool because of X, Y, and Z reasons. So I think the middle ground is actually quite nice. Yeah.
Is that why you do it? And I ask you this question especially because you work with climate and
Mhm.
you're studying the past. You know more than anybody else who could, more than I could, in terms of like what the future holds. Like you said, this is the reason why you study the past is to get some insight into the future. Is that
Correct.
one of the reasons why you're so passionate about getting the word out?
Yeah, I think well, I think everything's really cool. Like, I couldn't wait
Of
to start
course.
talking to you about isotopes, and I don't even think I set everything up, so I'm like, "Oh, so isotopes," and, so, I think it's really cool. I think, um, science is something that I think everybody likes the idea of science, but they don't always get the chance to learn about it properly. Let's say, like, you might learn it in high school, and then that's kind of it, and then you go about the rest of your life never really talking or thinking about science ever again. But I think there's still that interest. So I think personally, I really like talking to people about science in general, and I do like communicating these things because I think there are a lot of issues and topics that people are generally interested in, but it's just the science a lot of times just kind of turns them off because they haven't really spent that time thinking or talking about science. So when you start mentioning words like isotopes, or you start saying things like talk about orbital cycles, you lose people. So I think it's worthwhile trying to talk to people about this to understand the why, because when they understand the why, then they can almost have a better understanding of the entire issue as a whole. Like, instead of just saying, like, okay, don't drive your car so much because you're releasing fossil fuels and that's warming the globe, and then you're like, but why? So then, like, okay, well, because the greenhouse effect does this, 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 and this. And we know, like, as an example, looking at isotopes, we can actually see why that we know for sure it's fossil fuels that are being burned that are causing this. So then you can actually give them a better understanding and a better grasp. And I think people are generally appreciative of something like that if you can communicate it in a fun and like engaging manner, and like not talk down to people, but then at the same time not being so vague that like it's like, okay, like you threw some words at me and I still don't understand what's going on. Yes, again, I think there's a sweet spot. Sorry, go ahead.
I think transparency is the big one,
Yeah,
and non-judgment. I think that's, where a lot of scientists miss the mark. I can say that because I'm not a scientist and I'm not in academia, so I'm not I can always I don't have to deal with a lot of the bullshit that comes out of academia, but
fair
essentially
enough.
it's true. I mean, I think there's a being judgment free. I think you're right, just
Mhm.
explain it in terms, being curious and encouraging other people's curiosity
Yep.
is so beautiful.
Yeah.
And I mean, it's great that you're doing it. You mentioned cars as an example, which is really really fun because of the push now for EV cars and
Yeah.
electronic vehicles and all that stuff. Because people, like it or not, do have to get around.
Yeah.
They have to travel. It's great to one day you'll want to get to Greenland. Maybe we'll have electric planes. Maybe I don't
Yeah.
know if that's the future.
That'd be
Do
cool.
you think, as a scientist, that will make a big dent in fossil fuels?
To go to alternative forms of
Yeah.
fuel, like next gen nuclear reactors and things like that.
Mhm.
To a degree, yes, but I think we we need to stop releasing fossil fuels into the, like, I know it's not, but oil is the lifeblood of civilization right now, but um, we can do a bunch of these alternative methods which will help. But until we stop actually pumping things into the atmosphere, it's only going to help so much. Like, you can plant like a trillion trees, and yeah, it will help. But then if you look at how much carbon trees will capture compared to how much carbon we're releasing to the atmosphere, like, it's still dwarfed, right? So if you stop that input into the atmosphere, and then you start doing things like planting more trees and now these alternative forms of energy, like, then you're going to start noticing a difference. Then you can, let's say, try to mitigate some of those long-term effects of climate change. But even if all oil, let's say, stopped right now, there's still a lot of effects that are like still in the pipeline. So it's not like, okay, all cars and factories and cruise ships and everything, planes, everything are gonna stop emitting fossil fuels like right now at this moment. It's not like global warming is going to suddenly change. Like, there's still going to be some warming effects. There's still going to be some um, some consequences from the previous release, and then eventually, once all those effects from the pipeline are done, then maybe things can start getting reversed. But I think some things have also been, the damage is irreversible. So now it's a matter of trying to cope and move on, and try to find some form of normalcy while still kind of preserving the environment as best as possible, and also like people's livelihoods, right? Like even fishing industries and things, like fish are moving more north as waters get warmer, or just like migration patterns of animals in general change. So what does that mean for these communities that are, let's say, primarily composed of fishermen? Like, the whole industries can actually start to collapse, right? So now they need to try to reinvent themselves just to make a living. Like there's so many effects throughout the entire socioeconomic ladder that we need to consider. Sorry.
Yeah, it's, no, don't be sorry. It's
Yeah.
I mean, there are so many consequences to this stuff, and I'm
Mhm.
sorry I'm not talking more about isotopes, but
It's okay.
the thing that's really interesting to me is also something that you said at the beginning of the interview, which is that the Arctic used to be full of like alligators and things
Yeah.
like to me that's I mean isotopes are cool and all that stuff and but to me the big picture is what really fascinates me is this idea that there
Hmm.
used to be a time when
Yeah.
the Arctic had alligators and had like wasn't full of ice. Like that to me is what just blows my simpleton mind here. I'm just
Yeah.
like, wow. you so what the heck happened? Like I guess this was just the normal cycle of the earth and then it got followed up with an ice age?
Yeah. The Earth's entire climate history is filled with these cycles. Basically, like I'll talk about CO2. So a lot of CO2 in the atmosphere causes a warming. This also causes chemical weathering. So the CO2 in the atmosphere then actually mixes with the water that, and that will fall as rain, and now it's actually acidic rain, and then that actually starts to chemically weather rocks. But now some of these rocks actually end up capturing and retaining some of that CO2, and like they'll be deposited as like what we know today as, let's say, calcium carbonate or a carbonate of some sort, just because there's different types of carbonates as well. So then over time, that will actually start to remove CO2 from the atmosphere, and then we'll actually start to get a cooling. So as CO2 is gradually removed from the atmosphere, we get a cooling. Now, this happens over millions of years. This is not like
Of
a
course.
potential, yeah, like this isn't like
Thank you.
I've solved global warming. Just
Yes.
it's not anything like that. It's just yeah, we can wait millions of years and things will go back to normal, of course, but well, we may not be around as humanity at that point in time. But yeah, like so there's these constant feedback loops that will eventually start to um, change the climate. Or like in the example I gave before, where when these plankton get buried in the ocean and they're trapped, like that carbon that's now getting locked away from the atmosphere can actually mean there's more oxygen that doesn't actually end up forming CO2. And then over time, like then you also have these bacteria that like to reduce sulfate. And that's what they use for their food in redox conditions. But then they might start to deplete the sulfate. And then now there's more iron that doesn't have to bond with the sulfate to form pyrite. Now that iron's loose, and now we'll start to bond with phosphates. And now there's less phosphates in the ocean, which means the plankton don't live as much, like they don't proliferate as much. So now they start to die off. So now there's not as much oxygen removal, because a lot of times when they die, they decompose and they use up oxygen. And then if they get buried, then the carbon that they incorporate in their bodies is locked out too. But like you can get these cycles where now like okay, you oxygen can now get reintroduced into the system just naturally, and you could go from being a very oxygen poor environment to over time gradually going to um, like a dysoxic, which is kind of an oxygen low, and then you can eventually become a fully oxic environment again with time, and then everything's happy again. And then once again, you start getting more plankton proliferating, and then they slowly deplete the oxygen in the water column again, and then the cycle goes back to being oxygen depleted.
There's an old, George Carlin joke. I don't know if you've ever listened to the comedian George Carlin, but he said, "We don't have to save the planet. The planet will be fine. It's the
Yeah.
humans. The humans will just die off. Who cares? The Earth will be fine. She'll take care of herself." I
Well,
mean, it's a very really cynical look at life, but it is
yeah.
perhaps even a little true, right?
Honestly, yeah, it is true. Like we've had at least five major extinction events that have happened throughout Earth history, and like the Permian extinction right before the Jurassic, like 95, 96% of all life on Earth was wiped out, and like things are fine today, right? Like Mother Nature, or like if you want to treat Mother Nature, the Earth as an entity, like we'll be fine. Like Mother Nature doesn't personally care if like humans live on the planet, or if it's dinosaurs, or if
Right.
it's like humans died and now like squids evolve and now there's intelligent squids living on land. Like Mother Nature doesn't care. Mother Nature doesn't care about polar bears or if New York is underwater or anything like that, but we do, and there's implications that we face for that, right? Like we don't want to see species go extinct. We don't want to see certain industries go bankrupt, or we don't want to see these people get displaced, both in developing but also in developed nations. Like we don't want to see that, right? Like there's a lot of these, we don't want to have droughts because now like farmers lose their business and now there's less food, and like what does that mean? Or so there's a lot of like there's multiple tiers of society that are getting basically affected at once. So like that's mainly why we care about global warming. The earth itself will be fine. Yeah, the earth, like, has there's been at least 5 mass extinctions and earth is fine. It's just, what does it mean for society as a whole?
Yeah, humanity and the animal kingdom and all this stuff, right?
Yeah,
Is this so I wanna talk about you, personally a little bit here because 'cause we've got about
sure.
15 minutes left, and is this really, we've really been talking more about global warming than I thought we would, but
Yeah.
I guess, is this something really that you're obviously passionate about? Like, is this your cause, your raison d'être is this kind of education?
Um, I kind of consider myself um, I want to be like I consider myself almost like a modern Renaissance person. Like I like kind of like everything. Like I even paint. So
Oh,
it's
well,
like,
we're gonna get to that, but yes.
oh, okay. Yeah. So like I'm passionate about earth environmental sciences. This is my field, but like you can get me on another episode and we can like talk about ancient Egypt. Like I love ancient Egypt and I've taken courses on that, and I can talk to you all about Hatshepsut's journey to Punt, which is we think is modern day Ethiopia. Like or like astrobiology and astronomy, or just anthropology. Like there's a lot of different things that I have interests in. Like I'm fortunate that stable isotopes, my my bread and butter pretty much, is a very versatile field. Like I can take the tools I'm using right now to study climate change and use it to look at forensics, and like saying like, oh, like, looking at the carbon and nitrogen in a person's tooth can tell me about their diet, and then I can like roughly estimate if it's a missing person, maybe what their culture would have been based upon the diet that they ate, or where their geographic location is based upon the hydrogen isotopes in their hair.
Is this something you wanna do as a career maybe later on, is work in forensics? I'm just curious.
That's a really good question. Right now, I do want to focus on earth and environmental sciences, but one day, if I'm fortunate enough to have my own laboratory, I probably would branch out into forensics as well. Like try to have like, I would consider myself just like like a stable isotope chemist, not necessarily a geochemist, just like a chemist that now applies stable isotopes and things like that to problems throughout. Like human interest, basically. Like I have an archaeologist friend who found a little town in Rome, and I told him like, hey, if you found any bodies, like it'd be cool to do some like sulfur isotope studies on them, like, but like,
Cool.
yeah.
That's definitely, like, if you were to start doing that kinda stuff, I definitely would be like, "Hey, we're doing another episode and we're just talking about that," because that's
Oh
a
yeah.
whole other field, that's a
Oh
whole other
yeah.
branch, and it is absolutely fascinating.
Yeah.
You mentioned, painting, you also mentioned filmmaking in terms of
Oh.
interests, I saw that in your profile. I actually I have worked in filmmaking, for a while.
Oh.
I've kind of gotten out of the field because I don't think it's for me. I don't like working with other people that I can't necessarily choose
Oh,
who to work
fair.
with
That's fair.
sometimes. But I really did enjoy the actual experience of being a director, being a
Hmm.
producer. It's a really cool thing. Are you making films as well, or are you just kind of more of a film critic?
Um, as of right now, I'll probably just say more of a film critic.
Okay.
I do have some stories that I would like to have developed at least in written form. I don't know if that will ever develop in anything. Maybe I'll just end up publishing it as a book or a comic book or who knows. But like, I have like a horror anthology series in my head, or I have a fantasy series as well that I'd like when I'm maybe should be working on my thesis a little bit more. I might be thinking about this, um, or when I'm just like, okay, it's midnight. I'm gonna put my thesis stuff away, and now I'm gonna work on this for another like 2 3 hours because I go to bed at 4 a.m. now, thanks pandemic. Um,
I know the
so
feeling, so do
yeah,
I.
yeah, it's just now like that's my body expects it. It's like, no, no, you're not going to bed at 1 o'clock in the morning. You crazy? No, no, no. Put on a cup of coffee and let's start thinking about this thing. Like, yeah,
Yeah, I'm always looking out for the next Indiana Jones movies because I feel
oh
like
yeah,
there's not enough films being made about archaeologists and archaeology in general. I
yeah,
feel like there's a lack of that.
yeah. I think with the Indiana Jones films, there's a lot of untapped potential. Like, there's a lot of cool little MacGuffins from history that you can start to look at, or curses, or like whatever. Right, like the last movie, which I don't know if I even want to talk about, but we'll just say the last movie even incorporated aliens. But
Yes.
yeah,
Yeah, that one was a little special. I was not expecting it.
yeah, yeah.
So and then, just quickly before we do run out of time, is the painting because that is something, I interview artists, I interview scientists, and there is
Mhm.
absolutely a link between the arts and science.
Oh yeah.
I would love to interview someone who's actually studying that link. That would be really cool.
Mm.
Uh, Creativity and emotional expression is very different from the creativity and the intelligence that you use in science. Do you
Yeah,
find that you kind of get a different flow, let's say? Let's call it that, a different flow when you paint?
I think so. Actually, since we're talking about it, I help to organize. There's an arts and science talk that we're having at the university, and a creativity for scientists night that we're having next week as well with people in my department. Well, it's
What?
faculty of science wide, yeah.
Cool.
Um, I think there's a lot of value in the arts, and I think it introduces a mindset that a lot of people don't actually appreciate, especially in the sciences. Like, I feel like a lot of scientists are like, no, no, I only do science and that's it. And like, art is meant for artists, but there is like um, even just like skills of observation, like just something basic. Like, a lot of us are now used to like looking at something really quickly and getting that information, but like a painting actually can make you stop, and if you stare at it long enough, you'll start to pick up details that first 3 second glance that you gave it, you would have missed entirely, right? And you can start saying like, I don't know, it's a crowd of people. Okay, great. But then you start looking, and then you might start realizing like little trends, like, oh, like people on this side seem to be really sad for some reason. And like, why is that? And then you'll see like in the distance something is happening, or like you start to notice little details, or even things with shading, and how, what does that mean? Or even just a general appreciation of how the person who painted this actually thought about the shadows, and how trying to make it as realistic as possible. Or even in like in sculpture, or even if you don't even want to get something that's like, let's say, classic art, but like even like modern art, like a lot of these ideas and concepts that are being communicated, and it might look like something weird, like, okay, this person got a banana and they like nailed it to a wall and they put like red paint on, like, what does that mean? But then you think about their mindset and what they were trying to communicate, and if you spend time actually considering it, it could actually be something insightful that you never thought about. I
Oh, dude, we could have a whole talk about how conceptual art, in my opinion, ruined art, but whatever, that's my own
Yeah,
opinion.
yeah. Well, you know what? I kind of agree, but at the same time, like, I get it sometimes, like what
Mhm.
people are going for. Um, I tend to like more classical things, like how well can you represent nature? Like, when how detailed are the muscles and veins in this painting or in this sculpture? I tend to mainly paint nature stuff, but like you're just trying to replicate the human form. Like, that's so complicated, and if you do it properly, like it's amazing. Like, look at the David. Like, it's like stunning.
And putting your own spin on it too, that's part of art.
Absolutely.
It's not a purely intellectual pursuit, but I totally get what you're saying. Like there's an aspect of realism that
Yeah.
I'm not a realist. I don't like doing real stuff. I like painting from the emotional.
Mhm.
But it is an admirable thing
Oh
when
yeah.
somebody can reproduce the muscles and or put their own spin, like the group of seven and how they
Oh
painted
yeah.
trees. Like, oh my god, I don't
It's
know if you've
so
ever seen them in person, but oh. It is absolutely moving.
Yeah.
Um, on that note, listen, we're out of time, and I just want to say thank you for coming on the program. I
Oh,
mean,
thank you.
I can't even wrap my head around even this just the stuff we talked about. We didn't even deep dive into your topic of specialties, and
Yeah.
I feel like I already have enough to really start pondering at 3 a.m. As to what all of this means and what the possibilities are. So
Yeah.
definitely at some point we should arrange to have you on the show again. I think it'd be a lot of fun.
Amazing. I'd love that. Yeah.
Wonderful. Well, thanks again for coming on the program.
Thank you.